Topic of this YouTube video is finitely generated groups. What do you mean by a group? A non-empty set G with a binary operation star G cross G to G, Cartesian product of two sets, is said to be a group if the following property holds. First property is for any two element G1 G2 belongs to G implies G1 star G2 also in G. This property is known as closure property. Second property is for any G1, G2, G3, three elements in G implies that G1 operated with G2 and then resulting element operated with G3, and the same can be done for G2, G3 operated with G3 and the resulting element then operated with this G1. So this equality holds. So it means that there is a in a particular order it is immaterial it is immaterial to write G1 G2 first operate or G2 G3. So this property is known as associativity. Third is existence of identity. We can find there exists an element E belongs to G such that G E G is operated with E is G again, and when E is operated with G, this also gives G for all G belongs to G. So such element E is called identity element. When it is operated with any element of group G, it gives no change. So this element E is known as the identity element. It can be proved this is unique. Fourth is for any G belongs to G, there exists an element G dash belongs to G such that G dash when G is operated with G dash is E and G dash is operated with G is E. So this G dash is known as inverse of G. This element is known as inverse of G. In fact, the element here, the element G dash is known as the inverse of G. So it depends how to write G dashes depends on binary operations, which binary operation we are considering. The uniqueness is also there. G dash is unique with respect to G. So every element has its unique inverse. So it can be comment here. Every element has unique inverse. So it can be proved easily that. So another we have a situation when in a group G together with the binary operation star, if A star B equal B star A for all AB belongs to G, then we say G is abelian group due to Abel, mathematician named abelian group. So there is a two types of group we can classify this study. The types of group can be further classified abelian group. ठीक है, abelian group are those having the above property, and non-abelian group. So this property is known as commutative property. So a group having a commutative property, then it is abelian, otherwise it is non-abelian group. So there is also another kind of classification, finite or infinite groups. Finite group or infinite group. So this should be noticed that if we will use we consider two types of groups here. Additive group. Additive groups means a group with respect to addition binary operation. Then addition may be addition of number, addition of matrices, addition of functions, addition of vectors, whatever be. So it is a additive group and multiplicative group. So like that, multiplication is also matrices, multiplication of two matrices, multiplication of two rational number, multiplication of two natural number. It doesn't matter. Yeah. So usual addition, usual multiplication. Sometimes we right. So this is in case of addition, we always consider identity element as zero element, and in case of multiplication we consider 1 when it is very much clear that the group has numbers, so we will use 1. Otherwise for arbitrary group, in case of arbitrary group we always consider multiplication, improving some results, because it gives us some comfort to prove the results. So it is quite easy to write AB instead of writing AB. So we will use multiplication operation in most of cases when we develop the study of group, subgroup, normal subgroup. So and it is both things are synonymous. If there is a additive group, that can be considered as a multiplicative group. So the main difference is that the identity element here written is 0 and here written is 1 or E. In case when we have to write inverse of, so what is this? It depend upon the additive identity. So additive identity is 0, then inverse will be negative of that. So A, inverse of A. Inverse of A is minus A. Here inverse of A is A raised to power minus 1, because here we write A inverse equal E, or here we will write A plus minus A is 0. So these are notational. A plus E. A plus A in addition. In multiplication we write AA. Therefore in particular we A plus A can be written as 2A. In same way A into A can be written as A square. We can write A plus A is 3A, and A is A cube. Like this, if we are adding A n times, so we can write NA. We are multiplying n times, we are considering operation multiplication, then we will write A raised to power n. There is another interesting situation is NA equals 0, or here an equal to 1. If such situation appears for some finite number n, then we say order of element is finite. So order means the least positive integer satisfying this condition, then the least positive integer is called order in case of additive, and in case of multiplication the least positive integer satisfying this condition. Like example, iota raised to power 4 is 1. So and we know that iota raised to power 12 is also 1, but 4 is the least integer satisfying this condition, so 4 is the order. So such structure is also useful to describe the notion of order of an element and order of group, and several other concepts of group that are useful in our study. And similar A minus B can be written as, okay, A minus B is 0 means A equal B, A equal B. So here AB inverse is 1. So what it will be concluded? So there will be another kind of approach that we always consider. So B is minus A. Okay, B is minus A. B is inverse, can be taken as an inverse of A. So minus B is minus minus A. This is again A. In same case of this, A inverse is again A. So this also can be seen in a group minus A plus B can be written as this. It seems absurd, but there may be a case when addition can be this type of addition is not commutative. So we are familiar with this notation, but we are not familiar with the notation. But both the notation are uh, mathematically equal, okay, in consideration of operation of these. So now we come to our topic, finite group. So a group is said to be finite if G is finite. G is finite, and infinite if G is infinite. So the finiteness or infiniteness is depend upon the underlying set G. So example of infinite are there. Set of integer is an infinite group, but it is finitely generated group. But it can be seen that it is finitely, this is infinite group, but it is finitely generated. So topic of finitely generated group is quite important because infinite group can be finitely generated. We will discuss later on. So another example is you can take a group G. G can be taken as e raised to power n, or you can say 2 raised to power n. N is integers. So we can say that this is a group under multiplication. Okay, if you take two element here, A 2 raised to power n and B 2 raised to power m, both n and m are integers, then we can A into B is 2 raised to power k, where k is a sum of these two. So this is again integer whenever n m are integers. So there is a closure property, and we know that 0 belongs to z, and 2 0 can be written as 1 belongs to g, acts as identity element. And if you have a 2 raised to power n, then there exists a dash 2 raised to power minus n in G, such that a dash is 1. Okay, 2 raised to power 0 is 1 and a dash equal to a. So it can be seen that this is group. This is also infinite group. In fact, both groups are same. This group and this group both are same mathematically same. Such situation will be discussed in isomorphism of groups. So we can take an example of finite group. Finite group. So we can take an example of a group G that has element complex number and satisfying this condition 4 equal 1. So this we know that this equation has solution 1 minus 1 iota and minus iota, where iota is minus 1 raised to power this. So this is an example of a finite group. we can make a composition table of this group 1 minus 1 iota minus iota. The finite group can be it is for in a finite group with small order. This is a product complex product denote the binary operation of two complex number, and so this is a composition table. This is called composition table. Okay, this is composition table. So 1 minus 1 I minus I, this is minus 1 1 minus I, this is I iota, this is iota. We multiply this with this, and you can see here the result is, so if you multiply this with this, so we will get element here. So this is okay, this element is multiplied with this. Okay, this is minus iota, and this is a minus iota here, because this is iota multiplied with 1, and here iota multiplied with minus 1. So this is a very simple way to express minus 1 1, and this is iota, and you can see this is 1 and this is minus 1. So this is a composition table, Cayley table also known as. So we can see all the entries in table belongs to this set. So this is closed under multiplication, and we can associativity is there because of this is a set of complex number, and the whole complex number has is associative with respect to multiplication. So this is associative. One act as multiplicative identity. You see that this is same as first row. This and this are identical. So we can say this is one is the identity element. Identity element. Now we can see this column is also, and we can observe some certain things here. The first row is first column, second row is second column, and third row is third column, fourth row is fourth column. It means that it is abelian, because each row is a column. So or and vice versa. So this abelian group. So uh, as we have seen that set of integer is finitely generated, so every this is a finite group. So finite group, so we can find if obviously if we want to generate by a subset of, then there must be some element. It can be observed that 1 can be written as iota raised to power 4, minus 1 can be written as iota square, iota can be written as iota raised to power 1, and minus iota can be written as iota raised to power 3. So we can see that every element of this can be written as a power of iota. Iota raised to power k, k is 0, 1, 2, 3. So we can see that this is generated by this iota. It can be seen that this is also generated by iota. Student may verify. So, and it is not generated by 1, because 1 raised to power 1 is 1, 1 raised to power 2 is 1. So we can say that this group is generated by iota and minus iota. So what is finitely generated means? So we can say a group is finitely generated. A group is finitely generated. So let G be a group. It may be finite or infinite, and S be any subset of G. So a subgroup generated by S is the intersection of all subgroups of G containing S. We can say that if there is a family of subgroups H, H is a subgroup of G. And this family has a subfamily that contains S. Then G is said to be generated by S. G is said to be generated by S and written as this if G is this is intersection of all such subgroups. So this concept requires the knowledge of subgroups. We know that intersection of two subgroup is again a subgroup, so this is a subgroup, and in that case this becomes identical to this. So we can say this the group generated by a set, generated by a set, and this set may be finite or infinite. So if S is phi, we certainly have write this is equal to E because it is subgroup contained at least one element E, and in case of other particular situations, so we can say intersection of these subgroups. So this is the smallest subgroup. In fact, G is this is the smallest subgroup of G, which contains S, which contains S. So in particular, we can say if H is a subgroup of G that contains S, then H must be G. H will be G in this case. So a group generated by, or sometimes we can teach this topic in subgroup generated by this. I will give an example here. So like if we take a group G as an element 1 E, you can take E x y, you can take x square, and you can take x y, and this is x square y. You can take a group. So this is a set, and if we define binary operation like this, x cube is equal to E, y square equal E, and x y is equal y x square. Then with this operation, we can make a composition table. Then G can be seen as a as group generated by x and y. That is, we can take set x that contains two element, and so G is generated by S. Or sometimes we write G is generated by x minus y. It can be seen that E can be written as obviously uh, x square into y cube, okay, and x can be written as x cube, okay, we can say, and y can be taken as y raised to power 4, or simply you can x raised to power 1, y raised to power 1. They have several representation, then x square can be written as, okay, so you can x square, and that can be written also x raised to power 5. So has several representation. Also can be written as a x square y square y, like this also can be written as x y x. This representation also will be there, okay, x y y x, because y square is identity, so we can, and x y x1 y1 and x square y also can be written as x y y x y. Okay, so you can see that every element, so This can be written as element of this are x raised to power alpha, y raised to power beta. So we can here alpha beta can be taken as 0 less than alpha less than, you can take it, you can make a or you can say alpha beta are positive integer, including 0. You can or you can exclude 0 here. So this is notion of subgroup generated by subset, generated finitely generated. So element of this are somewhere. So elements of such groups, as we have seen, that can be written like if there is a group G generated by some, if G is a group generated by this set S. So if we have G is arbitrary element of G, then G can be written as S1, N1, S2, N2, SK, NK, where SIs are element of G which are in S. So and Ni are integers. In case of integers, when order of every element of S is finite, otherwise it has a different forms when Ni's can be written as a plus minus 1, because of the notion of inverse will be. So in case of if it is not finite, if it is not elements of S are not of finite order, so in that case we will write in such a form. This also can be discussed with the greatest interest. So this is, so I have already given an example of this. So in like this, if you we can consider H. H is a set of G1. You can, or you can write. We can, okay. Let S has certain element S1, S2, SR, ST, ST element. So it has T element. S has T element. So we can form a group here of elements that has element of the type S1 epsilon 1, S2 epsilon 2, ST epsilon T, yeah, you can say SK epsilon K, where epsilon I equal to plus minus 1, K is less than equal to T, 1 less than equal to T. Okay, so this is, so there is a 1 less than I less than K. So if we can prove that this is a, first of this is a subset of G, we can prove that A is a subgroup of G. We can prove that A is a subgroup of G. So we can write such elements. First of all, it can be shown that S is contained in G. S is contained in G and S also contained in A. In fact, because we can write S1 belongs to S, implies that S1 has a representation S1 1. So this belongs to A for all. So for each I, we can say Si is, can be written as Si1. So it is in A. So it is a finite representation of such type of number. So this is A is a non-empty. And if you take two elements of the type you like alpha, S1 alpha 1, S2 alpha 2, S K alpha K, and you can say beta S 1 beta 1, S2 beta 2, S L beta L. Then you multiply alpha beta Then this is again some element S1 gamma 1, S2 gamma 2, S S M gamma M. So this is a product of means gamma 1 is alpha 1 and S1, okay, gamma 2 is alpha 2 and gamma M, where M is can be taken as K plus L. M can be taken as K plus L. So you can see that this belongs to A. So A is closed under multiplication. Inverse of alpha also can be defined. Inverse of alpha can be defined as K minus alpha K, Sk minus 1 minus alpha K minus 1 and S1 minus alpha. So every element, this is again in A. So every element of uh, A has a multiplicative inverse. So therefore, we can say that so such a subgroup is said to be generated by this set S1, S2, S1. So our interest in this video is special interest when it G is generated by this. So as a subgroup can be generated by G, so adding more elements in this set, we can find a subgroup A that is equal to G. So a group also can be generated by its subset, as we have shown in the previous example. Thank you.